Of course, if we have the TS diagram, let's also make its block diagram, or a simple diagram that shows how this looks like in actual setup. So first of all, let's make the boiler over here. Okay, that's the boiler. Then this is where the tube towards the first expansion happens. Therefore, this is the turbine. Meaning, this goes back for the first reheat. Therefore, this is the first reheat. Then it ejects again to here. Then this is that state. Now the second reheat after expansion goes again to the boiler. Then again goes up again. So we have this 13. So this is 9. This is 12. And this is 14. Now going back to the boiler again. Then lastly it goes down to there. Last. Therefore we have divisions of the turbine are like this. There are 4 stages of turbine. Let's write that. Let's write its path also so we could not be confused. It goes there, it goes there, it goes there, and it goes there. Sorry, the drawing is really bad, but bear with me. So now, this happens. This is for research purposes or blocking purposes only. So of course, if we have a closed feed water heater, then we need to rejoin it to the open feed water heaters by a mixing chamber. So this is the mixing chamber. And so here we extract the first the closed feed water heater. Therefore, this is the box. This is the box of the closed feed water heater. Then it is pumped back to 15 MPa to the mixing chamber. So this now is a line to the closed feed water heater. Now another one here is a open feed water heater. Therefore, it receives this open feed water heater right here at 1.5 MPa. Therefore, we extract here. That's the open feed water heater. Let's write arrows over there so also. And yeah, this is the output. And also there are 2 inputs to this. Now we add a pump over here because the pressure here is different compared to there. So another open feed water heater. By now this open feed water heater is extracted at the turbine for heat. Therefore this is extracted here. So that's the extraction part there. Now the turbine goes, the final turbine goes to the condenser. This is the condenser. And there is pump 1. Then pump 1 moves it down there. So looking at our diagram, or let's place arrows first. Diagram should not be looking like this, but similar to like this, because this will help you in guiding to where you can do mass balance and energy balances. So therefore, we can now label this based on our drawing. This is 12. This is, this is 9. This is 10. And this is 11. This is 8. This is 1. This is 2. Oh, this 1. This is 2. 3 is the output. This is 15. this is 4. This is the output, so this is 5. This right here, or this point right here, is 13. And this right here is 10. This point going back in is 12. This is also 13. That's also 13. That's 12. So this thing coming inside of the closed feed water heater is also 10. Or just 10. Because they have the same enthalpy. Because of the bleeding. But the difference is that there is a mass. There is mass in here. Therefore, they have the same enthalpy, but the amount of the mass is not the same. Therefore, their energy is not the same. Energy value is not the same. So now this is after the boiler, so let's expect this is 17. So this, here we have 1 as the mass. Now here we have 1 minus mass 1. Then 1 minus mass 1 minus mass 2. Then 1 minus mass 2 minus mass 3. 1 minus mass 1 minus mass 2 minus mass 3. So here is a really rough sketch. Let's just name it the boiler, a mixing chamber. And this is pump 1, pump 2, and pump 3. Oh, we lack pump also here. We lack a pump here. So pump 4. Plus minus. Yeah, you can get the point. It's a condenser. This is an open feed heater. Another open feed heater. And a closed feed heater. Let's just scale this down so they can do the calculations now. So with that, and I also simplified with that. Now I simplified this so it's much easier to look at. So now, first of all, we need to calculate the masses of these things. So the mass of the bleed at the first bleeding, the second bleeding, and the third bleeding. So now we need to get mass 1. So how do we get mass 1? First of all, we need to look at this junction right here. That junction signifies that there is a mass or energy balance happening because there is exchange in energy in the system. So if you look at that, this is the closed feed water heater. So looking at it, if let's draw it again, closed feed water heater. Oops. This is the closed feed water heater. There is an input here, and there is an output. So this open feed water heater. So the enthalpy here is, the state here is 10. The state here, prior, is 6. Is 6. That's 6 right there. That's 6. It exits 6. It exits at 7. This is 7. And this is 11. So if we do energy balance, here, so energy at 10 plus energy at 6 is equal to energy at 7 plus energy at 11. Meaning, all input is equal to output. Because we assume that the system is perfect, no losses. So all input is equal to output. If we expand this, H10 mass, so what's the mass there? Mass at 10 is M1. Because if you look at this, this is the mass, and the mass right here is mass 1, M1, plus H6. What's the mass of H6? H6 is right here. And we know H6 has a mass of M2. But the problem is that, or not the problem, but what happens here is that if you're going to look at this, meaning that the mass here and the mass here joined together. Therefore, the mass there is only lacking of 1 minus M. So, 1 minus M1 is equal to H7. If you look at this part right here, H7 M. So what's the mass of H7? Still the same as H6. 1 minus M1 plus the output of H11, which is M1. We have values of H10, H6, H7, H1. Therefore, we can solve to find the M1 as the missing values. So now we can calculate it using our calculators. So we're going to input H10 M1, which is 3152. So let's write it here. 3153.25 times mass 1 plus H6, no, not bad. H6 is at 684.99. 1, no, there's a plus over there. 1 minus mass 1 is equal to H7. So what's H7? In an ideal system, H7 is equal to H11. For always, this is a reason if you're having a ideal cool speed water heater. Therefore, H11 is 0.87. Yeah, so 0.87.31 times 1 minus mass 1 plus H11 is still the same, 0.31 times mass 1. So using your calculators, you can solve for mass 1. So what is mass 1? So inputting I'm still inputting in my calculator also. We could derive that if you want. So now we have mass 1 as 0.097%. 97. Therefore, mass 1 is only 9%. So we keep that value. So we keep this value for now. So we store it there. So we got mass 1. Now, how do we get mass 2? Mass 2 can be seen in this equation, in this particular part of the drawing. Here. If you look at mass 2, if you're going to look at right here, then you are going to have an energy balance here. So if we are going to draw it again, I'm going to draw it at below. So this is another feed water heater. This one and that one and that one. There's only 3 because it's an open. Therefore, this is the entrance, this is the entrance, and this is the exit. And we know that the entrance to that is 6, and we know that the upper one is 13. And its output is 5. So doing energy balance again. Energy balance will lead us in H input mass of 13 is M2, right? M2 plus H6. What is the mass of H6? If you're going to look at 6 here, oh no, not 6. That's 6. Oh no, that's the output. 4 rather, 4. My bad. This is 4. This is 4. So, that's 4. So, mass at 4, if you're going to look at the TS diagram, is mass 3? No, it's not mass 3. Because we're looking at here, then we are looking at, because this is state 4. So, H4 is equal to H3. 1 minus mass 1 minus mass 2. Why? Look at 4. Look at 5. 5 is a collection, or let's just complete this one. H5 is equal to 1 minus mass 1. So great. Why is H4 1 minus mass 1 minus mass 2? So 4, this is really confusing. Oh well. That's H4, this is the 4, this is 4. Oh wait, did we change it? So here's the new one. This is the input for 4. This is output. Mass 3 cancels out. Because here, mass 3, the mass 3 and mass 3 here has been sufficed. Therefore, what's left is 1 minus mass 1 minus mass 2. Which leads to this equation. So now we know what H13 is. So we plot it right here. So H13 is 3325 times mass 2 plus H4. What is H4? H4 is 605 plus 605. 0.93. 1 minus, we got M1, which is 0.97. 0.097. That's 1. Right? So 0.097 times, lacking, minus M2 is equal to H5. What's H5? H5, we did not include H5 over here. Okay, forgot. So what's H5 over here? H5 is, using the steam table again, because I deleted it. Sorry, my bad. Using the steam table, it is 1.5 MPa HFG. Therefore, at the saturated pressure table, so at 1.5 MPa, it has 844.89. 844.89. So goods. 844.89 times 1 minus 0.097. So doing this, we got the mass balance now. So we only have the unknowns of M2. So now we can get M2, which is, using a calculator, input 3325 times M2 plus 605.93 times 1 minus 0.097 minus X, or M2, is equal to 844.89 times 1 minus 0.097. So we got a smaller one, 0.08. So 8% was mass 2. So that's really small extraction, which is really good considering that there's a big mass that is getting heated and reheated all the time. So now we have mass 1 and mass 2. Now we're going to find mass 3. Same principle again. To find mass 3, we are needing to find this specific part, or looking here, that is the mass 3. So therefore, if you're going to draw it again, let's draw it over here. We got entering of 15 and the entering of state 2 exits at state 3. So energy balance now is H15 and H15. So looking at 15, where's 15? H15 M3 plus, what's our input? H2. H2 is where? Here. And it's running with 1 minus mass 1 minus mass 2 minus mass 3 is equal to its exit part, which is H3, and H3 is running at mass 2. Therefore, mass 2. But first, we need to look at what happened to H3. So, H3 is a collection of a... If you're going to look at this specific diagram, H3 is where we eliminate M3 and M3. Therefore, what happens here is that H3 now only lacks of M3. So 1 minus M1 minus M2. Because H3 was sufficed here. This is mass 3 here. And it was sufficed there. So it was sufficed by H15. So that's why the output here is just like that. So now we have the enthalpies of this thing. H15 now is 3231.90 times mass 3 plus what's H2 is 192.22 times 1 minus 0.097 minus 0.08 minus mass 3 is equal to what's H3? 604.74, right? Times 1 minus 0.097 minus 0.088. So now, we can now find mass 3. So finding mass 3 yields us with substituting it all, 3231.90 times mass 3 plus 192.22 times 1 minus 0.097 minus 0.08 minus mass 3 is equal to 604.74 times 1 minus 0.097 minus 0.08 is equal to mass 3's extraction was really big, 0.111, yeah, 112 kilograms, or yeah, the fraction. Therefore, we got mass 1, we got mass 2, and we got mass 3. Therefore, because we're having this one, we can now solve for everything. So let's erase that thing. We can now solve for Qn, or the heat applied in the system.